Thank you very much, Professor Banerji, for the very generous introduction. I would also like to thank you and the governing body of the foundation to invite a somewhat impure organic chemist for the 9th Oration lecture. I unfortunately was not part of this Calcutta University during my student days. I did not do my master's here, but of course I was aware of the phenomenal work done by Professor Chatterjee and her group. But I unfortunately also did not have a chance to meet her or talk to her during my the early part of my independent career here. But it is indeed an honor and privilege to be able to speak today as part of the 9th foundation lecture of Professor Asima Chatterjee Foundation. Thank you very much again for this honor. What I would like to do today is to tell you about a story that evolved naturally over the course of last 13 years or so. And I must tell you that about 15 years ago, I would not even have imagined talking about this particular theme. So in case this title seems a little confusing, I would like to highlight the middle part of this phrase in a couple of slides from now. So I will talk about a very simple analytical technique that evolved as a function of time, as I said, during the last 15 years or so, and the types of analytes that we have been able to analyze are all shown here. And let me group them into 4 categories in the next slide. Here they are shown again, somewhat scattered, but let me get them in some order. So what you see here is a natural product, extract, and I thought that it is most fitting that I spend some time talking about the analysis of a natural product in connection with the great tradition of this department. You also see a few drugs here, and I will show you what classes of drugs these are. In the 3rd row, you see several enzymes, and I will talk about them a little bit later. And last but not the least, in the last row, you have small molecules such as formaldehyde, hydrogen peroxide, and last but not the least, a glass of water. So you might wonder that what is the common theme by which all these types of analytes can be detected using a simple technique. So as I mentioned, I would like to highlight this phrase of what I mean by photoluminescent sensor platform, and that is nothing but a gel or a gel-like material derived from bile salts. So what I will do in the next 4 or 5 slides is to give you a broad background on bile salts and gels. Incidentally, bile salts are also nature-derived products. Although they are derived from mammals, largely commercially they are produced from ox bile. So let me just give you a brief introduction to bile salts and acids. It turns out that 95 years ago, Heinrich Wieland got the Nobel Prize for his research on bile acids. And bile salts were in fact discovered in 1848 by Strecker, whose name is associated with the Strecker synthesis. It turns out that although the Nobel Prize was given, the molecular formula was correct, but those of you who are even remotely familiar with the steroid structure would recognize that this is not the correctly known steroidal structure. Because what you see is that the rings are fused in a somewhat awkward manner. There's an ethyl angular group, which is of course not true in the real structure of the bile acids. In the next slide, I will show you the correct structure of bile acid or bile salts. These are also known as biodetergents or biosurfactants, but they are a bit different from normal surfactants in that they are facially amphiphilic. The top face of the molecule has the hydrophobic face. the bottom face is lined with 2, 3 and sometimes 4 hydroxyl groups, making the bottom face or the alpha face somewhat polar in nature. And there is a side chain ending with a carboxylic acid, which is frequently conjugated with taurine or with glycine to make them more water soluble. So it acts as a detergent and can help, thank you, and can provide a variety of physiologically significant functions. For example, for solubilizing the fat that we eat and make them accessible to pancreatic lipases. So bile salts are produced in the liver by series of oxidation processes involving cholesterol and are stored in the gallbladder until the food, when you eat, until the food reaches the early part of the stomach, the duodenum. I will not go into these details, but enough to say that the bile acids play a very important role in the metabolism processes. What are gels? Of course, there are many who are familiar with small molecule derived gels, particularly in this department and in many other departments. In the last 20 years, there has been a lot of advances in using small molecule derived gels. But let me go back a bit and talk about polymer gels, because polymer gels have many real life applications. They are used in food, cosmetics, medicine, and many other applications like wound healing and so on. These are some commercial products that you frequently see in different places. But it turns out that small molecule derived gels have received a lot of attention during the last 20 or 30 years. However, to set the record correctly, I would like to show you that the first description of a small molecule derived gel was in 1841, published in this journal by Lipowitz, and this is a German, but what he talks about is the lithium salt of uric acid forming a gelatinous mass under certain temperature and solubility conditions. Although it was reported in 1841, not much attention was given to small molecule derived gels until the late 1980s, because the techniques to study these gels became more easily available from the 1980s and 1990s, particularly the microscopy and rheological techniques. And the first book on small molecule gels was published in 2006. All right, so with this introduction, let me now go back to a century-old paper and what triggered the work that essentially I would like to describe to you today. So this is a paper published in 1914 by a British scientist named Shriver, where he reported that the sodium salt of cholic acid, sodium cholate, which was known at that time, when mixed with calcium chloride sets to a gel. And the way the gel was described, it was described as a clot, okay, because it almost looked like a blood clot. So we became interested in this report, and the idea is that when we mixed sodium cholate with calcium chloride, it sets to a gel, as you see here, so the paper, the work was reproducible. But then the point that we tried to ask ourselves is that, all right, calcium forming a gel with cholate is fine, but in terms of a metal ion, calcium is very unreactive. It's very useful for us, but it's unreactive. So we asked ourselves the question that can calcium be replaced by other metal ions? If it is a reactive metal ion, then we might be able to do some fun reactions with those reactive metals while they are still embedded in the gel. It was not completely clear what would be the potential applications for that, but we thought let us check it out. And it turns out that we took this cholic acid and added various metal ions, and they all led to the formation of the gels. In fact, it turns out that it was initiated by a group of two students in my group. One was an undergraduate intern from St. Stephen's College, and the other one was my PhD student who happens to be in the audience, Dr. Orko Jyoti Chakraborty. And what Orko and Anjali found that by adding different metal ions to cholate, they set to beautiful, this is copper, cobalt, cadmium, zinc, silver, mercury, and this of course is our reference, calcium, which was made by others. So what Urko and Anjali showed in this particular paper published in 2012 was the material chemistry aspect of these gels, because they were able to make, well, Anjali left after a couple of months in the summer, but Urko continued this work, and what he was able to show is that you can make nanoparticles of different metals inside the gels, and these gels were all characterized by various structural techniques. So I will not talk about that today. At the same time, some other students, Supratim Banerji, who is now in IISER Kolkata, Sandeep Bhaumik and Ramesh Kandanalli, what they also showed is that the lanthanides also form gels with these metal ions, and that attracted our attention because many of the lanthanides are photoluminescent. In other words, they emit light when excited with UV or in the visible range. In particular, europium emits in the red and terbium emits in the green. And they have many applications, including they are present on the screen of the mobile phone that you cannot live without. So we thought that let us try to see whether these gels can be made photoluminescent, because as such these gels are not photoluminescent. And the reason for it is because the lanthanides have very low absorption coefficients, and secondly, the hydroxyl vibronic coupling leads to deactivation of the excited states of the lanthanides. So they do not show any emission in water. But people have got around this problem by ligating the lanthanide with a specially designed ligand for lanthanides, attaching it with a spacer, and then attaching an aromatic antenna. The idea is that the antenna will absorb light, transfer it to the lanthanide, and the lanthanide will emit, and the ligand around the lanthanide will ensure that water molecules are driven out, and they cannot quench the excited state by vibronic coupling. Now, this is a technique which has been very well known, and this is part of a review article published in 2009. And we thought that since we were able to make these lanthanide colate gels, can we think of a simpler way of making these gels photoluminescent? And the idea is the following. The gels, typically, they are like what happens when you put a ball of cotton in water. It soaks water through surface tension. Similarly, these gels, when you look under electron microscopy, you see these kind of nanofibers. Typically the fibers that you see here are between 10 and 100 nanometers, depending upon how you make it, what comprises of the material, and so on. Imagine that these green discs are the lanthanides located on the fibers. And it was also shown by my former student Samrat Mukhopadhyay, who is now in IISER Mohali, that if you have aromatic compounds which are indicated by these blue rectangles, they get embedded onto the fibers because the aromatic compounds are typically hydrophobic, and they get kicked out of water and they settle onto the fibers. So what happens by this process, when we take a lanthanide, colate, and an aromatic compound, is that they all come together spontaneously, and you don't need to make a complex ligand such as this. So the idea was, if this does indeed happen, then we might be able to have a situation by which a non-covalently bound aromatic compound or antenna will get excited, transfer the energy, and the lanthanide will emit. So what we have achieved by this then, if this happens at all, is that we bring together the sensitizer and the lanthanide through a non-covalent process. So the big question was, will this happen? And to cut a long story short, we found that these were again things which we had on our benchtop, and we tried, and the first thing worked. So we had some dihydroxynaphthalene, and when we doped it in the terbium colate gel, the gel became photoluminescent. So this gel without this sensitizer is not photoluminescent. It doesn't show any color when held under the long wave UV lamp. But when this is doped, it becomes green, and with pyrene and also with hydroxypyrene, the europium cholate gel shows a red emission. It's not strictly red because it shows a magenta color because of mixing of the red of terbium with the residual blue of pyrene. Okay, so this is the work that was done by Supratim, Ramesh and Sandeep. So we were very happy. But then the question is, do we stop here? Or can we make use of this lanthanide photoluminescence for some potential applications? So that is basically what I would like to discuss with you, and I will show you the rationale for which essentially has led to the design of a few types of sensors. First question was that, okay, fine, these molecules can sensitize the lanthanide and make them photoluminescent. But are there molecules with similar structural features in the nature, natural products for example, or drugs which will also make the gel photoluminescent? In that case, this technique would allow us to detect those classes of natural products or drugs. So that was one possibility. The second possibility, so in this particular example, we will choose natural products or drugs having similar structural features. Actually, structural feature is a very loosely worded term. Ideally, they should have the right level of triplet energy, because it is because of triplet energy transfer that the lanthanide is emitting in the process by a sensitization process. The other possibility is actually more interesting. Imagine that we have the sensitizer such as this, and that is making the lanthanide photoluminescent. But the question is, can you block the photoluminescence by some process, by a masking process? Can you mask, for example, these hydroxyl groups here or the hydroxyl group in hydroxypyrene and call it a pro-sensitizer, just like you have drugs and pro-drugs? In that case, you can design the masking in such a way that it can be unmasked or unprotected by a small molecule or by enzymes. And if you can design this process, then you will be able to detect such small molecules and enzymes by single technique, because you are always looking at the liberation or the release of the sensitizer, regardless of which enzyme or which molecule you are dealing with. I must also point out that this sensitization process does not happen in solution. It happens only in the cholate gels, not in any other gel. And we can discuss it later if the time permits. A third possibility is that we can now turn things around. The lanthanide makes the gel photoluminescent in the presence of sensitizer. But suppose I have a sensitizer and make a gel but with a non-photoluminescent metal. Can I now have a displacement assay by which I bring in a lanthanide that displaces the metal ion and makes the gel photoluminescent? Because that will enable us to analyze the lanthanides. And that is becoming more important nowadays, because many of your mobile phones will eventually have to be recycled. And when you recycle, you would like to know where the lanthanides are going, whether it is going to the environment or whether you are able to actually recover it. So we thought that it would be good to have a technique by which very easily you can detect lanthanides in solution, particularly terbium and europium, both of which are present on your mobile phone screen and in the electronics. So that would be a third possibility. That also requires the presence of the gel. Fourth possibility that somehow came together is the following. I will discuss it if time permits. What we found is that, and this has nothing to do with the gels, what we found is that these lanthanides in alcoholic solution, in methanolic solution for example, can get sensitized by certain classes of sensitizers, for example by salicylate. But if I add small amounts of water, the photoluminescence gets quenched. Okay. So again the question is, organic chemists are always afraid of water. In fact, some reactions do not happen even if you have small amounts of water. So we now ask the question, If I now have a dry solvent with a lanthanide and a sensitizer, and that shows photoluminescence, can I add now, can I titrate that with small amounts of water and see the effect? And can we indirectly quantify the presence of small amounts of water, say in methanol, ethanol, or in any other organic solvent? Because the way, perhaps some of you know that the way to detect small amounts of water in organic solvent is by Carl Fisher titration. And that's not something that is very easy to do. So we thought that by a fluorescence technique, can you find out very simply the amount of water in an organic solvent? If time permits, I will very briefly discuss it towards the end. But let me now go back to theme 1, which involves the detection of certain classes of natural products. And as I said, that I thought it is most appropriate that I spend more time on this because of the relevance of natural products to the theme of this foundation lecture. It turns out that there are many polyphenols, antioxidants, present in these fruits and, for example, in green tea. And they are all presumed to have good beneficial effects on your health because they are antioxidants and they can kill our reactive oxidant species and so on. Now, one of the components in cloves, for example, is gallic acid. And very quickly we found out that gallic acid can make this non-fluorescent gel fluorescent or photoluminescent. So gallic acid is again another sensitizer. It turns out, more interestingly, is that many of you drink green tea, right? Green tea has many polyphenols, and I will discuss that in more detail later on. But one of the major components in green tea is this particular gallate ester. It's called EGCG, epigallocatechin gallate. And in fact, this is a major polyphenol in green tea, and the quality of green tea is basically determined by the amount of EGCG present in the green tea. So this is routinely done for testing the quality of green tea by the commercial organizers, by the commercial producers. So this gallate, therefore, is doing something here that makes the gel photoluminescent. So we thought we will spend a little more time on it. So one of the things, what I show here is some technical data, and this is probably one of the very few that I will show because of the nature of the mixed audience. What I show here is the fluorescence intensity as a function of wavelength at different concentrations of gallic acid. This is done with pure gallic acid, no natural extract. And this is, the second one is done with pure EGCG, that is a gallate ester. And this is what is done by looking at the intensity of this major peak at 545 nanometer, which is the green color, as a function of concentration. And the spots that you see here are basically obtained by making filter paper discs, very low-tech science. You take a paper, you take a hole punch, make filter paper discs, coat them with the gel, look under UV light at by adding different concentrations of the extract or concentration of gallic acid and EGCG. And as you can see that the paper shows an intrinsic blue fluorescence. Some of you may have noticed it. But in the presence of gallic acid, it gradually turns greenish in color. And we measure it by a spectrometer, so we don't look at the blue color at all. And you can see a linear relationship, and the limit of detection of gallic acid turns out to be 300 nanomolar, and that of EGCG is 360 nanomolar, which is well below the concentration found in the natural product extracts. But then there's a catch. In this data, that I show here, we are only dealing with the pure molecules. So let's go to real life applications. So one of the things that we were concerned with is the presence of other components in various types of extracts which may have these gallate esters. So we looked at structurally similar molecules such as 4-hydroxybenzoic acid, catechol, dopamine, fluoroglucinol, pyrogallol, and of course gallic acid. And as the data show, and you can also see by looking at these colors, only gallic acid makes it green, and this is the actual intensity measured by a spectrometer. The other components did not show any fluorescence enhancement, showing that it is selective for gallic acid. Now coming back to the polyphenols in green tea, they are built on these two different molecules. One is catechin, which has the trans stereochemistry here, and epicatechin, which has the inverted stereochemistry at the hydroxyl. It is a cis structure. And the gallocatechin has this unit here, pyrogallol unit, and this is epigallocatechin. So this is called GC, this is EGC. And the corresponding esters with gallic acid. Okay, 1, 2, 3, 4. If you make an ester at this hydroxyl group or this hydroxyl group with the gallate, you get the other 4 components. And based on our findings, it's only the blue gallate unit will make the gel photoluminescent. In terms of the concentrations, however, not all 8 polyphenols are present in equal quantities. The major component, as I mentioned, is EGCG, which is 41%. This is an average number. And EGC, which is 14%. These two are too small. And the 23%, 11%, and 6% are non-gallated polyphenols, which we thought would not sensitize or make the gel photoluminescent. And as you can see that these two add together to about 55% of the total polyphenol content. So what we did is to analyze, is it some signal to me? Okay. So what we did is to analyze the tea extract independently and also to make a reference sample. As you can see, this is a mixture of authentic samples, gallic acid, catechin, caffeine, EGCG, and ECG. So we now have a reference chromatogram, and this is the HPLC of white tea. I'm not sure how many of you have actually drank white tea. White tea comes from the really tender leaves of the tea plant when they have not even turned green, and that has the highest level of polyphenol. And as you can see, that it has got caffeine, EGCG, and ECG. Green tea again has caffeine, EGCG, and ECG, but by the time you make black tea, because it is done by a fermentation process involving oxidation, all the polyphenols get oxidized. So while caffeine is still present, but there is very little amount of EGCG and ECG. So now we know how the extracts look like, how their HPLC profiles are. So we are now ready to test these extracts against the photoluminescent assay. And this is how it looked like. So again, I'm looking at the intensity of the green color. This is blank. B1, B2, B3 are 3 brands of black tea. G1, G2, G3 are 3 brands of green tea, and W1 is 1 brand of white tea. And as you can look at the intensities, that the black tea has very small quantity of EGCG or gallate polyphenols, whereas the 3 samples of green tea had significantly higher amount and white tea has a larger amount. It turns out the G1 in fact was a Taiwanese green tea which was sitting in our kitchen for a number of years, and presumably because of oxidation process the content of EGCG has gone down. But then there is always a question. We see some fluorescence enhancement. How do we know that it is because of EGCG? So side by side what we also did is to profile all these extracts by HPLC, looked at the intensity of the EGCG peak and plotted them together along with the fluorescence data. On the left hand side are the fluorescence data, the black curve. On the right hand side are the HPLC peak areas, and that is shown by the blue plot, and you can see that they follow one another, indicating that enhanced fluorescence is indeed because of the presence of enhanced quantities of EGCG. So that proves our point that the HPLC profiling matched with the, but then there were other concerns because tea extract will have many other components. So we checked the effect of other components such as caffeine, theophylline, catechin, epigallocatechin, which doesn't have the gallate ester, and of course this is EGC and this is EGCG. And as you can see from the data from the bar plot here, that except for the gallate derived polyphenols F and G shown here, other components did not show any fluorescence enhancement. Again, validating our analytical technique. The other idea was that, okay, fine, these components are innocuous independently, but when present as a mixture, do they affect the overall intensity enhancement? That also we tested by mixing 2, 3, and 4 with 6 and 7, and we found that they had no effect. And therefore, what we see in that green tea extract is really what happens based on our theoretical assessment. So non-gallated polyphenols did not affect the emission of terbium, thereby making this assay fairly robust. We also went ahead and made some clove extract. Clove can contain ellagic acid. Ellagic acid, in fact, is sort of a dimer derived from gallic acid, but it also has a biphenyl moiety. And we were wondering whether that would affect the luminescence. The other major component in clove is eugenol, which many of you know, it's basically an allylated phenol, but neither ellagic acid nor eugenol was able to sensitize the lanthanide fluorescence, but gallic acid did. So the clove extract can be very easily tested for the presence of gallic acid by our simple technique. And finally, it was also important for us to find out what is the cost, because when we submitted the paper, the editor said that how much does it cost to prepare one of these filter paper discs, which is coated with a gel. So we did a bit of arithmetic and on the economics, and it turns out that the cost of a paper disc at that time, about 5 years ago, was only 13 paisa. Okay, so you can get 7 paper discs for 1 rupee, and I think that's reasonably affordable in today's price. So to make a conclusion for this part, if you are drinking a cup of tea and you are not sure if it is green tea or black tea, you come to us, we can tell you in 5 seconds. All right. What about drugs? This was some work that was done by my student Laju Laishram, and Raju found that rather easily that there are a couple of drugs. One is a CNS active drug called propranolol, and of course many of you may be familiar with naproxen because it is used as a painkiller. It's one of these NSAID group of drugs. So propranolol has a naphthalene ring, naproxen has a naphthalene ring, and there are corresponding active molecules of the same category, like atenolol is also CNS active, but it has got a phenyl ring, and of course the very well known ibuprofen, which is also an NSAID, but it has got a phenyl ring. So our understanding was these two should sensitize, if at all. They will sensitize the fluorescence or luminescence of naphthalene, of terbium, but these two will not. And again, I will summarize in one slide. What Raju was able to show is that this terbium cholate hydrogel was sensitized by naproxen and propranolol, made the gel photoluminescent, but ibuprofen and atenolol did not show any fluorescence enhancement. So this made it possible to detect small amounts of these drugs, not only by when they are present in pure form, but we also did a spiking of blood, both blood, raw blood, and also blood serum, and we spiked it with these drugs, and we were able to show that these can be detected in small quantities. By small quantity, I mean parts per billion level. So this is selective, sensitive, and rapid. We are only using commercial ingredients, no background noise, and no sample pre-processing. I should also point out here, for those of you who are familiar with fluorescence, is that most fluorescent molecules that you are familiar with, they have fairly short lifetimes. The lifetime is typically a few nanoseconds. However, lanthanides have a much longer lifetime, of the order of several hundred microseconds to millisecond. So the advantage of lanthanide, and that's one of the reasons why we got into this business, is that you can excite the molecule and wait for a few hundred microseconds until the background fluorescence disappears. And thereby, even if blood has many other fluorescent molecules, you do not see or those fluorescent molecules do not show any interference with your assay. So that is the advantage, and that is what I mean by no background noise. More recently, my student Ananya Biswas, who should defend her thesis sometime soon, showed that these two second-generation fluoroquinolone antibiotics, norfloxacin and ofloxacin. Many of you in this region might be familiar with norfloxacin because it is often sold in a combination with tinidazole and is used for very severe upset stomach. So norfloxacin and ofloxacin, they both are structurally very similar, but they sensitize the naphthalene, terbium luminescence. And what Ananya was able to show that by making a terbium europium cocktail, I will not go into the details, you can find it from the paper. By making a terbium europium cocktail and by exciting at two different wavelengths, you can not only identify norfloxacin and ofloxacin independently, but even when they are present together, you will be able to do an analysis without physically separating the two components. So that was the advantage of this technique. Let me now turn to the third theme. The third theme was, or maybe the second one, was that I have a sensitizer that makes the gel photoluminescent, but I now want to mask it and find a way to unmask it by a trigger that will be an enzyme or a small molecule. So chemically that is a little more challenging, and that's what made things much more exciting. So we're now going to mask the sensitizer and see what happens when we unmask it in the presence of an enzyme first. And then I will show you a couple of examples of small molecules. So we chose these enzymes, the glycosidases, beta-glucosidase, alpha-glucosidase, beta-galactosidase, beta-glucuronidase, and then some other classes of enzymes, alkaline phosphatase, lipase, and beta-lactamase. The idea was that the top four are carbohydrate processing enzymes, and they are very important in our metabolism. And alpha-glucosidase, for example, hydrolyzes all the starch that we eat. And beta-galactosidase, or the lack of beta-galactosidase, causes lactose intolerance. Okay? Nowadays you see this commercially available lactose-free milk, which is done by incubating milk with an enzyme called lactase, which is basically a beta-galactosidase. It hydrolyzes lactase into galactose and glucose. So what we did very simply, I will not show the synthesis because of time. We took dihydroxynaphthalene and made a beta-glucose structure here, alpha-gluco structure, beta-galactosidase, beta-glucuronidase derivative, and for alkaline phosphatase, we simply took hydroxypyridine, made a phosphate ester. For lipase, we made a bispropanoate ester. I will not talk about beta-lactamase because the work is still in progress. And I will show you only one example of an enzyme catalysis. I will not show all the examples because they are all somewhat similar. So what we have now is a pyridine phosphate, and our understanding was that by putting the phosphate group, you are masking the hydroxypyridine, and it should not be able to sensitize the luminescence. Indeed, in the presence of the pyridine phosphate, the gel was not photoluminescent. Now we add alkaline phosphatase. Again, alkaline phosphatase is a very common enzyme, and those who have liver malfunction usually get tested for some other enzymes and alkaline phosphatase, ALP. We add ALP, it hydrolyzes this, releases hydroxypyridine, and now you see the gel becomes beautiful, gel shows beautiful red fluorescence. And this is the intensity enhancement at 617 nanometer. This is the red color. As a function of time, with enzyme, the intensity goes up. Without enzyme, the intensity does not go up. And a proof that it is because of enzyme catalysis comes from the fact that when I denature the enzyme, when I take the enzyme, heat it to 100 degrees for 5 minutes, and then do the incubation, there is no reaction at all. That clearly indicates that it is the enzyme action that is releasing the hydroxypyridine that is enhancing the photoluminescence. We also independently measured the concentration of hydroxypyridine and showed that the release of hydroxypyridine matches with the profile that we see by the spectroscopic measurements. Almonds, badam, also contain beta-galactosidase. So we showed that a simple extract of almond, one almond crushed with water, filtered, and added to our specifically designed substrate would show this beautiful green color in this particular case with the specific substrate. 1 and 2 are control experiments. So that was a quick way to detect the enzyme. Now, why do you want to detect enzymes? One of the ways is that the drug companies who develop inhibitors for enzymes, okay, a large number of inhibitors can be tested by our method, and we validated that by showing that indeed this beta-glucosidase inhibitor, which at that time was made by Professor Y.D. Vankar of IIT Kanpur. So he sent us a small sample of this inhibitor, and indeed what we showed is that the inhibition of the enzyme by this inhibitor can be detected by our method in a very quick and rapid method process. Okay, last couple of examples would be with small molecules. So for small molecules, you have to again mask the dihydroxynaphthalene in a way that the unmasking process will be triggered by the small molecule. So that we found a bit difficult initially, but then one of my students at that time discovered that biphenyl carboxaldehyde and the corresponding carboxylic acid, they are also sensitizers of the lanthanide. So in the presence of this in our colate gel, I must point out that again, without the colate gel, the enhancement of the photoluminescence is not very high. So biphenyl carboxaldehyde enhances the luminescence. So what my student Dipankar and Arnab did was to very cleverly converted this biphenyl carboxaldehyde into a homoallylic amine. And the idea is that this homoallylic amine was not sensitizing the lanthanide. But in the presence of formaldehyde, it forms the imine, and that immediately undergoes a aza-cope rearrangement, produces this imine, that undergoes hydrolysis, again releases the homoallylic amine and the sensitizer back and makes the gel photoluminescent. So therefore, we now have a masked sensitizer that gets unmasked by formaldehyde. And what they showed in this paper is that indeed you can show that in the micromolar concentration of formaldehyde, you can detect the concentration through the enhanced photoluminescence. And when we compare the limit of detection of our method with various other published methods, what we find is that our method actually beats most of them. Okay? This is 100 nanomolar, and some of these methods are typically in the micromolar concentration range. Where we still have to do some work is that this is done in solution, but we are now interested in looking at formaldehyde detection in the gas phase, because certain kinds of paints, when applied inside the houses, they release formaldehyde, and it is important that the concentration stays low. We have been able to detect microgram per liter concentrations, but we would like to go and make the sensitivity higher, and we are working on that. The second molecule, and this is work done during the COVID time, was hydrogen peroxide. And this work was done by Arnab, and what Arnab did is very simple. Again, as I mentioned, the biphenyl carboxaldehyde is a sensitizer. So he simply made a boronate, phenyl boronate ester with it, And what happens is very similar to hydroboration oxidation process. This molecule, upon interaction with hydrogen peroxide, makes it borate. Borate undergoes a deboration process, releases the hydroxy derivative, and that kicks out this quinonoid molecule and liberates the sensitizer. So again, what we have achieved by this process is a small molecule triggered liberation of the sensitizer and thereby making it photoluminescent. So again, the data showed that it was detecting small amounts of hydrogen peroxide, and we thought that we will make it COVID appropriate, because at that time, you may remember, all of us used to carry these hand sanitizers, and some of the sanitizers also contain 0.125% of hydrogen peroxide, not for killing the virus, but for killing bacterial spores, which can otherwise affect the quality. So we picked up 5 random samples of sanitizers which is reported to contain hydrogen peroxide, and we tested by our method, and you can see very clearly that 3 of them turned green, 2 of them did not turn green. Okay? And when we look at the concentration, this is the concentration, let me change this one. Yeah, so this is the concentration as per the label, 0.125%. 3 of them were okay, 1 had 0 hydrogen peroxide, 1 had very little quantity of hydrogen peroxide. So with this data, we were able to quote unquote sell it to the publisher, and without too much of a difficulty, because that made it COVID appropriate. So one last example, now it is the 4th type where I make a gel with a non-photoluminescent metal ion and now bring in the lanthanide, so that we can now detect the lanthanide by a displacement assay. So this is work done by Dipankar Bhaumik, and what he eventually chose was this M was a yttrium. You know, yttrium is a non-lanthanide, but it behaves as a pseudo-lanthanide. It also has a 3+ charge. So we make a yttrium cholate gel, which is not luminescent, and add either europium or terbium. We found that europium was much more sensitive in this particular case, and again, if you look at the limit of detection, except this one, which is a colorimetric method about 50 nanomolar, which is pretty good, all other photoluminescence data are actually much higher than ours, and what Dipankar was able to show that the europium limit of detection was actually 300 picomolar, less than 1 nanomolar. So that also made this work quite appropriate for detecting small amounts of europium. I still have 5 minutes left, so maybe I will talk about a little bit about the other work on detecting water. It's okay? All right. So this will be not by enhancing luminescence, but by quenching of luminescence. Okay. So this is the work done by my students Ajay Kumar and Manoranjan, and the background, as I mentioned earlier, is that the lanthanide, when surrounded by water molecules, can be made photoluminescent by incorporating salicylic acid. And by doing some optimization, we found that if I use a mixture of 2.5 millimolar of terbium, 0.1 millimolar salicylic acid in anhydrous, strictly anhydrous, which is also called bone dry methanol, it showed very high photoluminescence. But now what we do is we started adding small amounts of water. And as you add water, water gets around the lanthanide and it starts to quench. So you can quantify that. And as you can see here, the terbium salicylic acid in methanol is showing this beautiful spectrum that you see there. In water, the line is absolutely flat at the bottom. Okay? So water, no photoluminescent. Methanol, high photoluminescence. So we're now going to see how this peak gets affected when you start adding small amounts of water. So this is how it looks like. This is the intensity of this peak, and as you start adding 0.4, 0.8, 1.2 up by 2%, almost half the fluorescence is gone. So I will cut a long story short because of the time. This is how we essentially determined the amount of water percentage in methanol ethanol, acetonitrile, and in THF. These are again common water miscible solvents where the presence of water can affect your reaction. In THF, for example, a Grignard reaction if you are trying to do, or in acetonitrile, some other type of reaction which gets quenched by water. And we were able to make these linear plots with different coefficients, and ultimately the conclusion is that you need to have the pure sample. You don't need cardfish at titration. You need to have the pure and hydrous solvent, and you need to make only 2 fluorescence measurements that will allow you to detect the amount of water by looking at this plot or this equation. Finally, all these things are fine, but then there was also a question from an editor of a journal that, well, many of your measurements are done using instruments that cost thousands of dollars or tens of thousands of dollars. For example, this paper-based system that we showed were typically measured in a plate reader, which costs not less than $10,000 or $20,000. Can you make it simple? So one of the ways we make it simple is to take these paper discs, photograph them, transfer the image into a computer, and measure the intensity using an image processing software. Okay, so prepare sample, photograph under UV lamp like this, transfer to computer, and use imaging processing software. But then the question was, can we combine the steps 2, 3, and 4 together? So we eventually reached out to a company making medical equipments, and I'm happy to show you that the first generation equipment looks like this. That was designed as per our specifications. So this can do what I showed earlier, but in a somewhat semi-automated form. We have a small sample holder here, which is a 5x5 matrix, so we can measure the intensity. We can run 25 samples together. It has got 3 LEDs for different excitation of 275, 300, and 325 nanometer. It's got a blue filter, it's got a green filter, and a red filter, so we can measure both terbium and europium photoluminescence. And it has got a touch screen with a dedicated app that allows us to measure the concentrations. So what really started out as a simple exploratory project by Arko Jyoti and Anjali Das from St. Stephen's College eventually has brought us to this place, and we are seeing the possibility of having a practical application. And this kind of an equipment, this actually runs on a battery pack, and it can be used basically anywhere and everywhere. So if there is a diagnostic method that we can develop that can benefit the common man, then this can be a way by which this can be detected, perhaps at a much cheaper cost than using heavy commercial equipments. So with this, I would like to conclude my talk. I have only 13 seconds left as per my own clock. So I hope that I have been able to convince you that although the type of species I show here look very diverse, but we were able to find ways by which we can detect, quantify all of them, and hopefully some of these will see the light of practical application in the years to come. Last but not the least, in my red, now the timer is actually counting up. Some of the things that we are now working on, I should give you a perspective. One is to detect fluoride in water, because as you are aware, that fluoride and arsenic are very common problems. Arsenic is more of a problem in West Bengal, but fluoride is also a problem in arid regions. Small amounts of fluoride are okay, but large amounts are not. So we now have a probe for detecting fluoride in water using a photoluminescence method. This should be published sometime soon. We are also looking very seriously on antimicrobial resistance, particularly penicillin resistant bacteria. Typically when you have a penicillin resistant bacterial infection, you need to do a culture, throat culture for a respiratory infection, or urine culture for UTI, but that takes 3 days. So we now have a technique by which, in fact we have done it in a simulated urine sample using urine from healthy volunteers and spiking it with deadly bacteria. And we have been able to detect at least certain concentration of the bacteria within about 6 hours or so. So we believe that this can again lead to some real life applications. There is another enzyme called neuraminidase, which is implicated in certain types of cancer. We are looking at the detection of this enzyme as well. And something that is unconnected with this, but this is a very popular theme these days, is room temperature phosphorescence. This is something my student Arnab has recently discovered, again accidentally, and we are looking at some of these possibilities. So before I close, I would like to thank the key players. Anyway, Arkajyoti is here, so thank you Arkajyoti for initiating this project, which really has reached a different stage now, along with Supratim and Sandeep. So this was a picture taken some time back. Some of them are around, some of them are not. This was a picture taken last year in our new lab. We moved to this lab about a year and a half ago. So I would like to thank all of them. And very recently, my former and new students surprised me by organizing a get-together. And here they are in my office. So thanks to everyone who have really made this possible. And I would like to thank IISc and SCRB for funding somewhat a blue sky type of a project, which perhaps would now satisfy them, because we are trying to see that it reaches some sort of a translatable state. And last but not the least, thank you again for giving me the opportunity to share with you some of our work. This was a picture taken during COVID, and as you can see, there are no souls in this on the street at that time. So once again, thank you very much, and I hope that I have been able to address some of the concerns. Thank you.
Okay. Thank you, Professor Maitra, for this wonderful lecture, very informative.